In the late 19th century, there had been an accumulation of evidence that light exhibited wave-like properties, and so the thinking went at the time just how sound waves were disruptions in the air and propagated through the air. Water waves were propagated through water. Light must also be propagated through something. And so the name given to this hypothesis was the ether. That was the medium through which light propagated. And Michaelson, in the late 19th century, developed an experiment to get concrete evidence for the ether and to measure the Earth's motion through it. So Michaelson did this by setting up an apparatus kind of like the one shown here. He had a sodium light source. Sodium light source here, which emitted sodium photons here, and it went to this partially silvered mirror at a 45-degree angle. So some of the photons bounced up and then back against this mirror, and then some of them went through here, passed through. And again, the other group of photons, they passed through the mirror, bounced through this mirror, and some of them bounce back here to the view piece. So they all come out of the same light source, bounce, and then are recombined. And so the idea is, if light does propagate through the ether, these particles are being dragged with the ether, and then they have to swim against the ether, whereas these particles or photons have to go at an angle and come back. And the way Michaelson proposed to view these was through looking at the interference pattern of light. So this is an actual image from the view piece he was using. You could see the kind of stripe patterns, that's interference patterns. And the idea behind interference is that for constructive interference, the two wavelengths of the photons, they're aligned perfectly. So you have peak to peak, trough to trough. You get a big peak and a big trough. Whereas if they are 90 degrees out of phase, as shown in this schematic here, the peak is lined up with the trough is lined up with the peak. They're going to cancel each other out. And what this looks like mathematically, you can write it as L1 minus L2. So these are the distances traveled by the photons. If it equals n, for n is an integer, times the lambda, the wavelength of the light, so that's peak value to peak value. That's constructive interference. So if it shifts, these are lined up perfectly, you're going to get constructive interference. Whereas if you have this same expression, 1/2 n times lambda, that means that they're in this orientation. You're going to have destructive interference. This is also sometimes written as 1/2 plus n times lambda. It's the exact same thing. It's just a different way to write this, since n can take any integer value. And so he was looking at a pattern like this. And I don't know why actually the photons produced this particular stripe pattern for this experiment, but the main point of the experiment is that it produced a change in the pattern. Alright, so I should have drank water before I started this video. Instead I drank coffee. Alright, so the point of the experiment is what he wanted to measure the time traveled, the time difference from this path and this path. So we can use velocity times time equals distance, and if you don't believe me, get in a very fast race car and drive for a very long time, you will have gone very far. So let's just go ahead and get started right now with the mathematics. He's traveling for path length 1. We want to find the time traveled. So t, from this we get t equals distance divided by velocity. Alright, so t1 equals, now we're going to start with the path there. We have distance divided by velocity. Velocity going there is velocity of the light, c, plus v, because it's moving along with the ether. But then it has to travel back. and it travels by the same distance, and in this case it's moving against the ether, so it's minus that velocity. Alright, so this should be L1 in the numerator here. So we can simplify this, do a little cross multiplication. We got a nice conjugate there in the denominator, and the numerator is also not too bad either. And we're going to rewrite this right now, and it'll become apparent why we decided to rewrite this in this way in a minute. We can rewrite it as 2 divided by c times 1 divided by 1 minus v squared divided by c squared. So 2L1 over c. And I'm looking at my notes to see if that is correct. And yes, it is. So I'm not going to do the algebra, but you can get from this to this by, looks like dividing c squared by both sides, and there's this c in the numerator. Anyway, you can follow along with that if you want. So that is the extra time for the particle to go from here to here. Notice we're not doing the time for the, and I keep on saying particle, it's photon. They didn't know they were particles at this time. That's kind of what this experiment is about. So the photon, we're measuring from here to here and back, and then from here and then back again. We don't care about this, and we don't care about this, because in these two portions of the experiment, the two beams, they're considered combined. They have the same travel time. We're only concerned about the difference in travel times. So the time to go through L2, we're going to use the same thinking, distance divided by velocity. So what do we put in this velocity term? All right, and here you need to think about it like you're swimming from bank to bank on a stream. So you are a swimmer here, and you're going to go swim to the opposite bank, and there's water flowing. If you try to swim straight across, you're going to end up having a vector going downstream. You're going to end up down here. However, if you devote some of your energy, some of your velocity component to the upstream direction, that'll cancel out the water which is dragging you down, and you're going to end up swimming straight across. And so that's the same kind of logic we're going to use here. We set up a triangle which will give us a component diagram. So this is the velocity, this is the light velocity going at c, this is the velocity of the ether, which is pulling the light in the positive x direction, and this is the actual velocity component, the sum of the two velocities. We use Pythagorean theorem, so we're solving for the adjacent side of this triangle basically, and that's not right. It's going to be the hypotenuse squared minus this opposite side squared. The square root of that, that's going to be this velocity component, the actual velocity, if we sum up these two components. And that'll be the time to bounce there. Now on the return direction, actually the math is the exact same, so we can just double that. Boom, right there. And again, because we're going to use the binomial expansion in a little bit, we're going to rewrite this, factor out a 2, and we're going to take a c out of the denominator here. And we're going to have L2 in the denominator, 1 minus v squared divided by c squared. And so these forms are going to be very nice for the math that we're about to do here in a second. What we want is our delta t. So we want this, or t2 minus t1. t1 minus t2 would also work, but we're going to do t2 minus t1. So they have this common factor, 2 divided by c, and then we have L2 square root of 1 minus v squared over c squared minus this second portion, which is L1 1 minus v squared over c squared. Alright, so this is our delta t. So ultimately, if the two particles are combined over here, they're going to be out of phase. If they're in phase here, there's going to be some delta t it's going to take, I'm not sure which is which, but it's going to take this one longer, this one longer. So when they recombine here, they're going to be out of phase at this point. Now we're not concerned about whether or not they're in phase here. We're going to see in a second when Michaelson rotated his experiment, that's what we're interested in. So you can just take note of this delta t right here, and we will go ahead and rotate the experiment. So we take the experiment, rotate it 90 degrees, which is what he did. You could have also waited 3 months, I guess, and it would have rotated itself by the motion of the Earth, but I think he just did it by hand. Anyway, and it's the exact same thing here. I'll just write it out, delta t prime. I'm not going to do the algebra, again, for the sake of brevity, but it's going to look like 2 divided by c. And in this case, the L2, which you see here, this is L2. It's really difficult to see because I drew it really faintly. This is still L1 and this is still L2. So L2, again, the math is the exact same. You're going with light and then you're swimming against it. And this is going to look like 1 minus v squared over c squared minus L1. Here you have L1, and now this has the square root component because you're swimming perpendicular to the motion of the river of ether. Okay, and we're interested in the change of delta t. I'm going to talk about how that's significant in a second. So we have delta t minus delta t prime. Now, again, brevity. So what does this mean? 2 divided by c. When you end up doing this, and you can do it by hand if you want, if you don't trust me, but you're going to be able to factor out L1 plus L2, which is very convenient. It's very cool mathematics here. You're going to have 1 minus 1 over v squared over c squared, and 1 divided by 1 minus v squared over c squared, and this is the square root in this term. Great. And then why do I use curly brackets here is because I like fancy things and they look fancy. So we're going to rewrite this real quick as 2 divided by c, add up the 2 lengths, again referring to this length and this length. And then we can rewrite this using exponents. To the minus 1 minus 1 minus v squared over c squared to the minus 1/2. Now we use the binomial expansion at this juncture, which states that 1 plus or minus x to the n equals 1 plus or minus nx plus or minus n minus 1 divided by 2 factorial x squared dot dot dot. So we're going to use the first 2 terms in the binomial expansion. We're going to use the first 3 terms for the first one just to see why we really only need to use the first 2, okay? So we have this is a constant. We're not going to worry about that. And we're going to use this expansion to expand this out, and we're going to use this expansion to expand this out. So real quick, this plus or minus here, this plus or minus, if inside here it's a plus, that means this is plus, plus, plus. If inside here it's a minus, it means this is a minus, a minus, minus. That's what the corresponding plus or minuses mean. So let's expand out the first term. 1 minus v squared over c squared to the minus 1. So we have 1, it's a minus, minus n, which is a minus 1, times x, and our x here is v squared over c squared. All right, let's do the third term real quick, just for fun. Minus n is a minus 1 multiplied by minus 1 minus 1 divided by 2 factorial times v squared over c squared, and that is squared. So we have a minus, this will be a minus 1 is minus 2. Minus 2 times minus 1 is a 2. Times minus 1 is minus 2. So we have minus 2 over 2 factorial, which is going to be minus 1. So this is the main point, though, right here. The velocity with respect to the sun is the velocity of the Earth around the sun is 3 times 10 to the 4 meters per second. The velocity and speed of light is 3 times 10 to the 8th. So light is much, much faster than our velocity here. And so this number, v over c, this ratio here, that is a very small ratio. The number is very, very small. And we square it, we're going to get an even smaller number. And if we square that, we're going to get an even smaller number. So the more terms we have in this expansion, the more insignificant each term is. The only real significant terms here are the first 2 terms. And that is all we're going to use. So let's expand this out, and we'll include the constant. Okay, so we just showed that the first term here is, well, let's include the constant real quick. L1 plus L2. We show that the first term here is 1, and I completely just forgot what it was. 1 plus v squared over c squared. Now, minus this term, and this is going to be similar. 1, we're using a minus a minus n. N is a 1/2. And I stated that wrong. 1 minus n, n is a minus 1/2. Times x, which is v squared over c squared. Bada bing, bada boom. Alright, so the 1's cancel out here. And you're going to have, so x minus 1/2 x equals 1/2 x. X is v squared over c squared. Multiply that by the constant, so we have 2 over c L1 plus L2 times 1/2 v squared over c squared. The 2's cancel out, and get rid of this. We're going to have our final expression here of v squared times L1 plus L2 divided by c cubed. And that will be the time difference for the particles going from this path and this path. That's the time difference. That's the majority of work here for this problem. So take note of that. And let's use the numbers that Michaelson first did in Europe when he did his experiment. So we know the velocity of Earth, moving around the sun, that's 3 times 10 to the 4 meters per second. The wavelength of sodium is 583 times 10 to the minus 9th, and the length of the arms in the experiment were about 1.2 meters. Alright, so first off, let's get that number. We have v squared, so 3 times 10 to the 4 squared divided by c cubed. C is a known constant, times 10 to the 8th. We're going to cube that, and up here 1.2 meters, 1.2 meters, so he built the arms the same length as each other. You multiply this out, you should get a time difference for these two particles. When you shift it out of phase, the time difference that is a result of that shift should be 8.8 times 10 to the minus 17. All right, real quick, let's get the period of sodium. Period is going to be the wavelength divided by C, 583 times 10 to the minus 9th divided by 3.00 times 10 to the 8th. We are going to get a period of 1.9 times 10 to the 15th. Okay, so what does this mean intuitively? This is the period of sodium, which means after 1.9 times 10 to the minus 15 seconds, it's going to go from peak all the way back up to its peak. And when rotating the machine, we should get a shift. So let's say that you are Michaelson and you are looking at, right where this indicator is, at a bright spot right there. So you're looking at that indicator, and you know that the two wavelengths at that point are lined up perfectly. How do you know? Because it's a bright spot. There's constructive interference. Now you rotate the machine, and it says you should get a shift. One of these particles should now be lagging behind the other particle. There should be a slight shift because this one took a little bit longer to get there. I'm going to exaggerate that. So in this case, if it shifted an entire half wavelength, this light spot would be a dark spot. Now, we want to find the ratio of this shift to its actual wavelength. Is it going to shift an entire wavelength? So the shift, according to our calculations, which we spent the whole problem doing, is going to be 8 times 10 to the minus 17 seconds. Compare this to the wavelength of the sodium, which is 1.9 times 10 to the minus 15th, which is significantly bigger, but we're going to get a value of 0.04. So if we're looking at this bright spot here, and it shifts just a little bit, I'm exaggerating a lot, but just 4% over this bright spot, which we saw normally, which we know that the photons were aligned at this point, should be slightly darker. And Michaelson knew he would be able to detect that. That's the shift he was expecting to see at this point. The problem was he saw no shift. And I mean, this was pretty surprising because he was trying to detect something, and it turned out he got the null result, so he wasn't able to find it. Academia was pretty intrigued with this result, this null result, that he moved to the Case School of Applied Science in Cleveland, teamed up with Morley, hence the name Michaelson Morley experiment, and tried to detect the shift again with a more advanced setup. And again, he got the null result. So this was pretty confusing, and it sets ourselves up for our next video, which we're going to talk about privileged reference frames and the consistency and speed of light. The point to take away from this video, if you didn't follow along in any of the math, is that there doesn't seem to be a medium which light propagates through. And you can imagine if you were at that time, you know that light is a wave. There's an incredible amount of evidence that it is, but then all of a sudden you can't find what it propagates through. And this was a pretty good experimental setup to determine what it should be propagating through, but we just couldn't find it. And so it confused people for a while, but in reality, people just didn't know how weird things were about to get. And so we're going to be looking at that in the next several videos on how the universe just gets weirder and weirder. Thanks for watching.